First year, all the instructors are alumni. That's what they are. All right, good afternoon, everybody. We have one more lecture of particle box. We're going to move next on Monday, Tuesday, to a different model. We're going to be looking at for particular chemical bonds, but we're not going to be looking at it from the perspective of electrons, valence electrons. All right, so you think about electrons being shared, covalency, ionic. We're not going to talk about the electronic properties yet. Very different topic. There, we're going to have to think about atoms first and how electrons move in an atom. Worry about electrons. What instead we're going to be thinking of is a nuclear motion of atoms. Right, the atoms as balls connected with a spring, stretchy bond, and that motion, which we call vibrational. We'll come up with this really nice model for the nuclear kind of motion of the bond. Just uses a spring. Right? The model is a spring, and it nails our theory perfectly. All right, really beautiful work. Really simple, elegant theory for vibrations. And I think it's a really good place to kind of transition into chemical applications. Because even though it's not about electrons, not really talking about the nature of a bond, tools that we learn with what's called the harmonic oscillator, which is an oscillating spring, the tools, just like in a particle box, are very pedagogical. It adds a little more complication that we didn't have before, but it allows us to kind of grow into the theory. And then it'll be very natural to move into hydrogen. Then we'll move into multi-electron atoms. All right. So what I want to talk about today, one last application, exploration of the particle in the box. I want to talk, last two lectures, they talk about position, concept of how particle in this box, whether it be an electron or an atom or whatever, how it moves, how it propagates through the box. We looked at that very carefully last class. I want to go back to energy. So remember, the first thing that we did, right, was we solved for these wave functions for our particle in the box of constant energy. We got these sine waves out, so that we get these wave functions that are normalized. And are quantized by this n number, called a quantum number. And each one of these is associated, each one of these sine waves, these quantized sine waves, is associated with a very specific unchanging energy. Which is the function of this n, the mass of the particular box. These are states of constant energy. And every time I put my system in this state, I'm guaranteed to have this energy, fixed energy. Right? And that has a trade-off. Right? What do we lose? What information do we lose about the particle when we measure its energies? Fixed energies, well, we lose positional information, right? The position density, if you know, the product of the localization of the particle in space is completely delocalized across the box. Now, it's not completely delocalized in the sense that it can be anywhere. It has some wave structure to it, right? So there are regions where there's high probability and low probability, like the ebbs and the flows of the wave density. But in general, it can kind of exist everywhere. It's really not a specified position. And in fact, you can't even necessarily identify these waves as, say, a position. It's a wave that's delocalized across space. And I showed you why that is, right? That energy is a function of momentum, right? This is an object that has kinetic energy. Its energy is entirely defined by its motion. And so what we're effectively doing by fixing the energy, measuring states that have constant energy, is we're measuring states that largely have the same magnitude of momentum up to a direction. Energy is p squared over 2m. That energy. So in some ways, solving for the states of constant magnitude of momentum, right? Which is basically a velocity, e squared. In classic, right? So it has something to do with the motion. the motional state of the thing in the box, and that's fixed to a specific energy. Right? And that makes us lose information about the position because of the Heisenberg uncertainty principle. This is always true. And again, if you're kind of like me and you don't like calling things after famous scientists who are problematic, this is just uncertainty. Hard to ignore Heisenberg's contributions to the world. And it says that the error in delta X is inversely related to delta P. So here in energy, in some ways, by fixing our states in energy, we're fixing kind of our momentum, right? Up to a direction and a phase. But it has something to do, right, with the error in our knowledge of the velocity of the particle, if you will, the wave velocity, the way it propagates, speed at which it propagates through the box. That's fixed here. And it says, well, if this is fixed, that means delta P is effectively kind of near zero. And so we don't really have a lot of uncertainty in the momentum to be fixed in. So that means, again, our uncertainty in X is infinite. Right? So by localizing our momentum, we delocalize our position and vice versa. Right? That's what we saw in the other case. When we localized the position of our atom in the middle of the box, we lost information about the momentum, right? Because what we saw was that the wave structure of a particle localized in a small region has many oscillating components of different frequencies. Right? So if you wanted to represent this particle that's localized in the center of the box initially, right, I'm holding the electron and popping it in, that wave function, that additional wave function, is actually a sum of many of these oscillatory energy functions. Right? It's many, many oscillations of different frequencies. And the more you localize the particle, smaller delta X gets, the more of these energy wave functions you need to add to represent your wave function. Right? It's basically a particle that's very localized is spread out over many energies. And so when you measure the energy of that very localized particle, sometimes it'll read it's in the ground state, sometimes it'll read in the first excited state, second excited state, third one. Right? There's some uncertainty to its energy. You get different values for its energy depending on when you measure it due to the statistics. So there's always this trade-off. This big trade-off between energy and position, momentum and position. And so then again, we're chemists. We think about structure, chemical structure. It's so important to us. It's about the physical dimensions of our molecule. It defines everything. And so you sit and think, well, why the hell would I even care about these energy items? Things in constant energy, if my physical understanding of the particle is a ball or something like that in a box, I've lost all that structure information. And instead I have this information about energy. I've lost this information about the position. Why would I even do this? What's the advantage to going to a representation of constant energy? Well, maybe there's a box we can create that measures these energy levels. Right? Maybe there's a measurement we can make that's not a positional measurement, but an energy measurement. Right? And then if we're measuring in terms of energy, the possible states our particle could be in are just these sine waves. Right? These states of constant energy. Either it's in the ground state or the excited state, the 10th excited state, 100th excited state, doesn't matter. But I'm guaranteed to measure the outcome of my particle will be one and only one of these. So if I have some sort of measurement device that allows me to pick particles based on their energy, then this is a very useful representation of my molecule. And we have that tool. We have many of them in this department that do this measurement, that say, hey, I've got a particle, let's measure its energy. So the classic, the kind of prototypical energy experiment that we do is the one that you guys have been studying all this time. You might not have realized it. Spectroscopy. A spectrometer is a device that takes a quantum mechanical object, a molecule or an atom, and reads out something about the energy. Right? What do we see? Right? When we shine our light at some frequency or wavelength that's equal to the energy, the spacing between two energy levels to get an absorption or an emission. So all spectroscopy is, you're using light as a way to measure the energy levels of your system. So if you have a molecule that's in the ground state, shine light at it and it pumps it up to the excited state, you're doing a measurement on these energy items. The representation of your molecule from the point of view of light is exactly this. What it sees. So it's a very, very useful way for us to talk about molecules or problems, because it's exactly what light sees. This is the perspective on a molecule that light understands. Light is our measurement. So I want to talk today about this process. Very generically, what is spectroscopy? And let's do it on the particle in the box. All right, and we're going to learn a couple of really interesting things about spectroscopy that you may not appreciate learning it from kind of a qualitative kind of a little subtler you may expect. It's also universal. Okay? You can think about the different applications of infrared or NMR or optical, any other spectrometer you can think of. They all do the same thing, because they're probing different energy states. Infrared probes these vibrational energy states, the nuclear motion of the atoms. Optical frequencies, optical wavelengths, beauty is probing the motion of the electrons bound in these bonds, the motion of the electrons. And then you can think of other things like atomic absorption, photoelectron spectroscopy. There you're using light to do some sort of ionization. Using light to create an ionic state that you're probing. And I do an NMR, you're probing the spins of the nuclei of the hydrogen. Right? But the technique is exactly the same. Right? All you're doing is you're just changing the characteristic of the energy levels that you're looking at. Change what we call changing the degree of freedom, probing some sort of motion in your system. But the process is precisely the same. You're probing a series of energy eigenstates that have fixed energies, and they're interacting with the light. Every spectroscopy is exactly the same. This is the characteristic that these wave functions represent. Now, we haven't even discussed the fact that what I basically said is that the motion of the nuclei is separate in some way from the motion of the electrons in the bond. And that's different than the NMR, the spin. They're all in some way separable motions that we can probe separately, right? We pick different techniques and we see different motions. We haven't even convinced ourselves, and maybe it's not all that immediately obvious, there's no convincing reason to think that there are separate energy eigenstates. Vibrations and electrons, rotation, spins. Right? Why isn't it not just this giant series of states where all of these characteristics are shared together? Meaning when we excite something from one level to another, all of these things move. The electrons move, the nuclei move, the spins move, everything is getting excited. And that may be true. There's nothing stopping us from making that assumption. But what we're going to realize when we get to molecules is that all of these degrees of freedom, vibration, electron, rotation, translation in space, spins of nuclei, these are all effectively separable motions. Right? They can all be treated separately up to a level of approximation. Eventually, what we realize is that we can choose, based on the energy of our light, which motions we care about. And effectively, they're all separate from each other up to a limit. We haven't got that yet. But so let's do spectroscopy on this particle in the box, right? Which is just basically what we're doing is we're using light to give the particle in the box a kick. Right? Remember, higher energy just means higher kinetic energy. We're going to use the light to just give it a physical kick, get it moving. Right? But first we need to talk about what light is. What is the thing that's interacting with our system? All right, so let's just do a very, very simple structure or a very simple design of our experiment. Let's pretend that we have a molecular system that can be represented by a particle in a box, right? Here's my cyan. All right, and this is just a particle. This is, say, an electron inside of a box. Right, it's a molecule. Maybe it's a molecule that's got a single valence electron that we're exciting with light. But it's some system that can be represented by a single particle in a box. And what we're going to do is we're going to shine light at it. We'll have to talk about what the structure of light is and what it sees. All right, so here's my light. I'm going to define, we're going to do some simplifications. I'm going to say that the light is propagating along the x-axis. Right, so the light is coming in this way, along one direction. And the light will represent as a vector the field or the electric field of this light, E, x, which is a function of the position and time. This is my light function, my electromagnetic field. And just like our waves, our quantum waves, our wave functions, light is also a complex wave. It has two components, a longitudinal and a transverse oscillation. So we can write it as E to the I, k times x, minus omega times. So there's an oscillation that happens in space. Let me rewrite this for you really quickly in a simpler form. Right, this is cosine k times x minus omega t plus I sine k times x minus omega t. So we have this wave that, again, if you just ignore the imaginary component for now, we don't really have to worry about it too much. It's just a cosine that moves in space at some frequency k, and also has some time dependence, time frequency as well, temporal frequency. That's a function of time. Let's try to relate these two numbers together. What does it mean for something to oscillate in space versus oscillate in time? Let's write down a few things first. So k, this frequency in space, if you will, is what's called the wave vector. And it has a really simple formula. It's 2 pi divided by the wavelength of the light. Okay, so the light has some length scale lambda, right, which is just the distance from one peak to another. Right, so k tells you kind of how fast the system oscillates in space, right? So as lambda gets smaller, the wavelength gets smaller, the frequency increases, right? Right, and then we also have this omega. Omega again is the time, is the temporal variation in the sine wave. And so we can always relate omega to lambda if we want. Remember that omega is how many radians it spans per second. And this is going to be 2 pi nu, which is the frequency in hertz, which is 2 pi times the speed of light divided by the wavelength. Okay, so omega is related to the spatial variation of the wavelength as well. It just tells you how fast it propagates in time versus in space. So let me explain this in a very simple way. What's the difference? I'm just going to kind of cram it over here in the brain. So imagine I'm on a stool. And I'm going to sit here with my little detector. Right? And I'm going to measure this light wave propagating over me. And so here's my wave. This is my electric field. This is my light wave. And the difference between omega and x, and so the difference between the spatial part and the time part is the spatial part is how, with my rangefinder, right? This is the x component, right? This tells you basically if I freeze time, and I'm standing here and the wave is just passing over me, K tells you how far in space the next wave, the next peak is. Right? So it tells you something about the spatial component, right? How far do I need to walk from this point to reach here at constant time? It tells you about the spatial variation. Omega t is the time it takes for the next wave to hit you. Right? So the amount of time it would take is 2 pi omega, delta t, 2 pi omega, as this wave is moving in time with some velocity, which is the speed of light. All right, so you can see how the spatial oscillations of the wave are related to the temporal oscillations of the wave, in the sense that if the wave is moving at the speed of light constantly, then its spatial wavelength is the same as its temporal wavelength. Right, you could certainly have waves that are crunched in space but not in time, and vice versa. Okay, so we're talking about a wave that just acts very normally in space and time. So that's what my molecule sees, right? So when my particle in the box sees this wave that's alternating in space and time as it rolls over the box. So now the question is notice that I've drawn this without any sort of length scale. We have to think about, what does the box look like, or what does the wave look like to the box? Maybe a good question, right? So let's think about the length scale of lambda versus the size of a typical box in chemistry. Okay, because the way I've drawn it there is that my length is about the same length as the wave. Right? If I turn myself sideways, I'm about as long as this wave, right? So this is like a 2 meter long wave. Okay. But let's think about waves for spectroscopy. What are their length scales? And what's the length scale of a typical chemical system that's standing right here? If I put my particle in a box here, what we're going to see is that this perspective on a wave is not particularly accurate from the point of view of our particle in a box. Right? It's actually much simpler than this. So let's think about that. So first, let's think about length scales of boxes. The radius, for instance, of a helium atom is about 3 angstroms. Okay, and a carbon-carbon bond length, which is what an electron would sit in, for instance, is about 1.5 angstroms. Right, remember that an angstrom is 10 to the minus 10, since it's 3 times 10 to the minus 10 meters. Okay, so again, most of our chemical boxes are on the order of about an angstrom or a nanometer, which is 10 angstroms. All right, so let's just say that, right? So let's just say roughly our box scale, so L in our case for a particle in a box, for chemistry, is around 5 angstroms, or half an atom. Right, that's very typical. All right, what are the wavelengths of light that we choose? Well, if we're doing UV vis, right, green light is at 632. Sorry, 1064, 532 nanometers. If we're in IR, our wave is much longer, probably around 5 microns, which is 5,000 nanometers. If you're me and you do microwave, our waves are even longer. They're about 5 centimeters. And if you're doing NMR, even longer. They're probably closer to 20 centimeters or lower. Or let's say, actually, no, let's make that even bigger. Let's just say 50 centimeters. Okay, so and remember, this is the distance between two peaks, right? These are the wavelengths. Okay, so this tells me something about the distance between the top of one peak to the next one in space. Think about, again, think that your box is like a wave pool, right? And you're thinking about the distance between two waves. All right, so the highest energy or the shortest wavelength that we're ever really feasibly going to do kind of traditionally in spectroscopy is on a factor of 100 larger than the length scale of our system. 500 nanometers versus 0.5. Sorry, that's 5,000. That's 1,000 times 1,000. Right, so the length scale, so L over lambda, if you will, or let's say lambda over L, is at least a factor of 1,000 or more. So by thinking of a wave, light wave from the perspective of our box, think of it as like a little wave in the kinetic and what we call the Long Island shore. What's it called? Long Island Sound. Think of it as little waves on the sound, right? They may be like 2 or 3 feet tall. They can come up to your knee or something like that. But that's not what we're talking about here. Here I'm talking about a wave that's about the height of the bird you buy. Even taller than that, right? If I'm 2 meters, that's a 2,000 meter tall wave that's hitting me. That's about 5,000 feet. Actually, it's about 2 bird Dubais. Bird Dubai is about 2,600 feet. So we're talking about a wave from the point of view of the box, a wave that is astronomically massive. It's all that scene on the water plane and Interstellar, the giant waves that are moving. Think that, right? That doesn't look like a wave. Like the Interstellar, maybe I'll show you. You guys haven't seen that. I'll show you. If you remember the waves in that scene, the waves don't look like the waves that you see people surfing or the ones that you see in the ocean, right? It looks like a giant brick wall of water hitting about to hit you, right? It's just straight up and flat like this. And part of that is because of tidal effects from the black hole on the planet. That's a different together. But that's the idea that I'm looking at, is that you don't really see any of the curvature of the wave. All you see is this giant brick wall that's going straight up, and you can't even see the top curvature because it's so far up. Right? So really what the perspective that we should be looking at is that if this is my little box, psi, well, let me make it even smaller than that. This is my little wave function, a little system. Right? The waves come at it not like sines, but just like straight lines. Right? There's a peak here, and then at wavelength lambda, there's another giant peak here that just extends. This. And there's going to be another one. Right? So you're just getting ass blasted by this massive wave that has no structure to it other than it's just ridges of intensity. I mean, of course, there's going to be a negative facing one as well, right? So you're going up and then straight down and up and straight down. But let's just think about the top part of it. Again, they're going to be a half wave, like negative. Right? So these are what are called plane waves, right? They just look like planes of energy, planes of electromagnetism rolling over the system, right? It doesn't really look like a wave. It just looks like a straight, right? A two-dimensional plane. Or a one-dimensional plane. Well, from the point of view of you looking straight on, it just looks like this giant sheet of light on the torch, right? So it's a two-dimensional plane. You can approximate. It doesn't have any curvature. All right, so how does this simplify our explanation? Right, so the point of the matter is that the spatial variation of the wave means nothing. Right, we don't really care how the wave varies in space. The only thing we care about, right, is the time gap between each of the beats. Right, there's going to be some time, delta t, which is 2 pi omega, where you're going to get hit by this massive wave that doesn't curve at all. Massive from your perspective, it's just a giant wall. So the spatial variation of the wave is not only the temporal variation. So from the point of view of our box, from the point of view that's from only the POV of our particle in the box, the electric field doesn't really have any spatial variation. It just looks like time. Right? It's some initial amplitude E naught cosine omega t. You don't have to worry about the spatial. Doesn't matter. All right, so we can get rid of the x. We just have to worry about the time. All right. Now we have to think about the other perspective. What does the box look like to the wave? And this is, of course, very important because if the box doesn't interact with the wave, it's just like some neutral, boring billiard ball that doesn't interact with the electromagnetic field. The wave's just going to pass through it. Right? If it just doesn't look like anything an electromagnetic system can interact with, it's just a neutral, uncharged, boring billiard ball of nothing, the wave's just going to pass through it without any change. So we need to assume that if the electromagnetic field is going to interact with our system, that it has some structure to it that looks like something that can be interactive with electromagnetic field, which means it has to have some charge, right? It has to have some negative and positive charge. It has to have some charge to it. So let's think about that. So again, pretend that that side here is a molecule, representing a molecule with some electrons in it. From the POV of the wave. Right, our little side. Right, some molecule with some funky shape. Hope I'm not moving. Oh, thank God I'm not. Okay. And think about it as like a molecule, right? There's going to be some negative charge, right? Some like electronegative atoms that withdraw the electrons and negatively charged. It's going to be a positive region of your system. Right, so we could kind of like color this in with the positive regions and the negative regions. And so you've got maybe you have some positive charge up here. Right, and you've got some negative charge down here. In these regions. Right, and maybe there's some neutral regions in the middle. Like a zero charge. Right, you can think of that, right? So maybe you got some oxygens here and hydrogens here. It's a charge distribution. All right, and again, so the way if the wave were on the length scale of the molecule of the box, then it would matter if the wave hits this part of the molecule or this part of the molecule, right? The wave looks like this. Let me just kind of draw it. If it's a very high frequency wave, low short wavelength wave, right? Maybe it looks like this, right? The light is going to interact differently here than it interacts here. So this is where lambda is on the length scale of L. Right, so depending on the trajectory of my light for this really high frequency wave, depending on the trajectory of my light, the light's going to see a different charge distribution. If it cuts through here, it only sees negative charge. If it cuts through here, it's only positive charge. Cuts through perpendicular, obviously you can see a little bit of both. And so depending on the angle of the light versus the angle of the molecule, you're going to get a different response. And whether you have a lot of electrons or few electrons. Okay, but that's with the wavelength is on the length scale of the system. And here it's not, right? It's thousands, orders of magnitude. Right, so but for for pi over L, or sorry, for lambda over L much greater than 1, what does it actually look like? Well, it's this little box that has length scale L.
And all we can say is that maybe there's some positive charge here that's accumulated and some negative charge here, so that we could kind of write this as like a dipole. Okay? We've got a positive charge here and a negative charge here, and it's connected by a little pole, like a little bar of length L. So we can treat it like a dipole, right? Because the molecule, because the light, if you will, is this big, right? Like that, right? So it doesn't really see, it doesn't have any knowledge of the intricacies of this electronic structure. All it sees is that you've got some charge distribution, positive and negative, right? So here it only sees a dipole. Right? Now, if you don't know what a dipole is, I'm sure you've heard this in Gen Chem. Again, I like to think about bar magnets, those little magnets with a plus and negative charge. Or in elementary school, same concept, right? You have a place of positive, where you have a positive charge potential and a negative charge potential, and it interacts with the magnetic field and aligns with it. Same concept, except it's electricity. Electric field, not the magnetic. Okay. Electric field, magnetic field are very similar. They're just perpendicular to each other, like momentum and position. And you can have an electric dipole or a magnetic. And this is all electric, right? We're not doing magnetic. So we don't have to worry about the complications. We don't have to worry about the intricacy of the electronic structure. This method, we just sort of blasting this thing, and it looks like a positive dipole. Potentially, it could be have no dipole either. It could be fully neutral, no charge distribution. Like if this were methane, for instance, right? We'd have a problem. CO2. CO2 has no net dipole. But let's just say we can create a dipole. We can induce one. Doesn't matter. We don't have to worry about this. Let's just say it works and it is a dipole. All right, so what happens now? So what we have is this series of plane waves that are propagating at some frequency and some speed, interacting with an electric dipole, which is our system. So let's set up our spectroscopic problem. All right, so let's set up, first of all, we need to define our system, our box, in terms of some energies. Okay, so let's just pick a very simple substate of the particle in the box. So we're going to let our little molecule, little box, be particle in a box. A little psi 1 and a little psi 2. Where C1 squared plus C2 squared is equal to 1. All right, and these are, again, this is the ground state of the particle in a box. And this is the first excited state. All right, so we're just going to look at two levels. Right, just two levels of the infinite levels of the particle box. Right? We can do it for all of them if we want, but let's just focus on two. All right, so the way that I would draw this with an energy diagram, of course, is I have an energy, I have a state here, n equals 1, at energy E1, and I have the state n equals 2, at E2. And we can calculate an energy difference, of course, between them. Delta E, which is E2 minus E1. Right? And then what we can do is to use Planck's law, which says that E is equal to H times the frequency. So this means that delta E is V2 minus V1 over H. Frequency difference of the two divided by H bar. Or we can write this in terms of angular frequencies, omega 1 over omega 2 divided by H bar. Okay, and I'm just going to call this frequency difference, right? Each energy is associated with a wave of specific frequency, E1 and E2. We're going to call this omega 1, 2. Okay, so this is the frequency difference between the two states. So what I'm going to do is apply my spectroscopic condition, which is that I'm going to tune my light to be at the same, roughly the same frequency. Okay, remember, that's what we want to do. We want to get the wavelength of the light in the same energy difference between two energy levels, which means we're going to match the frequency of the light to the frequency difference of the two states. All right, so our spectroscopic condition, which we call resonance, is where the frequency of the light is basically omega 1, 2. Ideally, it needs to be right on. Turns out it doesn't have to be perfectly on. You can excite a transition even with slightly off resonant light. There's actually lots of really different things you can do with off resonant excitation. In fact, it's one of the ways that they cool molecules down to nanokelvin is by resonating, by exciting and burning off the hot molecules, which have a slightly shifted frequency because they're moving fast because of the Doppler effect. You excite them and they burn off from heat, leaving only the cold molecules, and slowly you drop the temperature. So you can use light and apply energy to take hot molecules off, bring your temperature down to nanokelvin. So there's lots of really tricky, cool ways you could play with resonance. And that's called sympathetic cooling or laser cooling. There's a Nobel Prize, I think, in 1997 for this technique using lasers to cool molecules. It's kind of strange, right? You're applying energy to something to remove energy from it. Very exothermic, which is very cool. In fact, the guy who won, one of the guys who won the Nobel Prize, Stephen Chu, was our during Obama was the head of the Department of Energy. We actually had scientists in scientific positions at one point in this country. All right. All right, so what I want to think about now is so we've got this light shining at this energy difference. Let's think about what happens. What can we compute about what happens to our system after we shine the light in? All right, so we have two options, or we actually have three options. All right, so what happens? Well, we could start, right? Well, the first one is our system, our molecule is in psi 1, which means it's in a ground state. And then you shine light at it, and it gets excited. And you end up in psi 2. Okay, that's a reasonable thing, right? We've excited our molecule. Another one is that it's psi 2. And you shine light, and it de-excites to psi 1. All right, this is called stimulated. The first one is called stimulated absorption or just absorption. This one, which seems kind of odd, you're using light to de-excite something, but it's the inverse of exciting it. This is called stimulated emission, which is what a laser does. All right, and there's one more option, which is that it doesn't do anything. Or psi 2 white. All right, we'll call that null, just a null event. All right, so the light's either going to send my molecule, it's not going to change the state of it, or it's going to change the state. Two options. We only have two choices here, so we don't have to worry about whether it's going to go to the next or third level or the fourth level. It's not worrying about that. So we can certainly go. So let's go ahead and let's see if we can figure out a way to calculate this. All right. So let's think about this quantum mechanics. Let's start with number one. How would we calculate this? Well, what I want to calculate, let me just bring this down. What I want to calculate is the probability that my system starting in psi 1 plus the light field, light interaction, leads to a output out of my machine into psi 2. What's the probability that when I interact the light with my state, my initial state, that I end up in the second? So we're going to use the same probability calculation that we've always done, that we've been doing on the homework, right? We're going to take some integral of our interaction operator, our measurement, which is light field, interacting with the molecule, and calculate its result on psi 1, and then project that result on the psi 2. So what that's going to look like, just like it does on the homework, we're going to have an integral over the box. We're going to first have some operator, which we haven't defined yet. We'll call it E light, with some interaction operator. And it's measuring psi 1. Right? We're applying it to psi 1. And we need to measure the probability. Right, this is going to return a vector, right? Remember, a vector times this is going to be some matrix, like this is color. We're taking a vector times color, that's going to output a new vector. And we want to calculate how that resultant vector from this measurement, how similar is it to psi 2? We're going to do some manipulation to psi 1. We might not do any manipulation to psi 1. It might end up being psi 1 again. But we want to see what the chances is when we do this that we end up in psi 2. Right, so what I'm going to do is multiply this by psi 2 right here. I'm going to stick a psi 2 right here. Right, so what is this doing? Well, this thing inside the parentheses outputs a new vector. All right. This is the vector or a wave function. If you want, I like thinking about vectors. I think it's a little easier. You have something that's pointing in some direction, and you want to know how similar it is to some other final vector that you're comparing it to, which is psi 2. You're going to take a dot product of this output and dot it with the vector, the final vector that you want to measure. That tells you the similarity between the output of the light field, the light interaction, its similarity to the final state you're calculating. So if this is 0, then there's no probability that when I take the light and interact with psi 1 that I end up in psi 2. It also could be 1, right? It also could be a large number, which means that every time I interact something in the ground state with light, it ends up in psi 2. Right? So this is some number. Okay, we don't know what the number is. We can calculate it. Right? Some number. Right? And we can do that for everything, right? For the next one, all we're going to do is swap psi 1 and psi 2. Because that one I'm interacting with psi 2 and then projecting my result on psi 1. And then here, number 3, I just have psi 1 or psi 2 on both sides. Right? Interact with the light with psi 1. What's the probability I end up in psi 1? And the dot product of vectors is an integral over the wave functions, which is why I have this integral. Right? It's the same calculation we were doing for averages in the homework a couple of weeks ago, last week. But now what we're doing is thinking about manipulation. What's the probability of manipulation? Taking the state from one to another. So now we just got to write this down, right? We haven't defined this light operator, this interaction, right? But we have all the components. All the components. All right, so let's work on it. All right, so what is E light? Interaction operator. Well, if you go back into, well, this is the interaction between electric field. This is just qualitatively, this is the interaction between a plane wave and a dipole. Okay, well, we have a formula for the plane wave. A plane wave is E of t equals some amplitude E naught, just the brightness of the light, strength of the light field, cosine omega t. And our dipole, if you go back to the dipole, it's just the charge times the distance between the charge. The idea is that you have a positive charge here on this part and a negative charge here. You have a total charge distributed charge separation difference of E, the charge of the electron. So number E times the distance. So the distance between the negative and the positive end. So the dipole has a very, very simple formula. Call it mu, which is the dipole, which is a vector, but it's only an x. It's going to be this number epsilon, which is the charge distribution, times x. This is the charge distribution between north and south pole. So if there are two electron difference between the north and south pole, this is going to be 2 times the charge of the electron. It doesn't matter, it's just a number. Every electron brings in a fixed amount of charge. You have some number difference between the positive and the negative charge, number of charges, and so it doesn't matter. It's just a non-zero number. And it's just a function of the position. Basically, the dipole gets bigger, the longer the apart they go. Right? And so if you go back into physics 2, electromagnetism, and you ask, what's the potential energy? What's the energy that you get, or the interaction you get between a light field and a dipole? Well, it's just the dot product of the two vectors. So this is just E of t, which is a vector in just the x direction, times dipole. The function of x. This actually has units of energy. This is an energy. It's electromagnetic energy, right? It's the energy of the dipole interacting with a field. Okay, well, I can just plug them together, right? It's just a function of time and x. It's E0 epsilon x cosine omega t. Right, something like that. Very simple. You have two numbers. These are just numbers about the properties of the two fields, potential of the molecule, strength of the field, mass, energy. Well, let's go calculate this. We have everything we need. We have a formula. We know the wave functions. We're just particle in a box. So let's go calculate these probabilities of transition. So let's think about the probability of taking the ground state particle, interacting with the light, and ending up inside 2. All right, well, that's going to be an integral from over our box, 0 to L. Side 2 is the second excited state of the particle in the box, which is 2 over L sine 2 pi x over L. All right, our interaction is E naught epsilon x cosine omega t. And then we have to apply that to our ground state, right? Because we're thinking about how the ground state goes to the excited state. Again, that's just 2 over L sine pi x. And that's integrated over space, dx. All right, so let's just simplify things out. Well, the interesting thing is that this cosine term just comes out. And remember, the light is resonant with the energy levels. So omega is omega 1, 2. We get this factor of cosine out. We get some numbers. Get a 2 over L, an epsilon naught, epsilon, just some numbers. And give us some sense of dimensionality. And we're left with just an integral of sine 0 to L of 2 pi x over L times x times sine pi x over L. Yes. Right, and that's an integral that we can just plug in and do. It's just an energy. And it turns out that this is non-zero. Okay? I won't calculate it. I have a little script at the program at the end that will show you a demonstration that will calculate this for us. But this is something that if we set L and some numbers, this is something we can put in Wolfram Alpha and calculate. All right, and it's non-zero. It's just a number. So the important thing is that let's just say that this is, we call this number, which is not equal to 0. We'll call it S underscore 1, 2. All right, so this is this S for the n equals 1 to the n equals 2 state. It's just some number. Right? We have a special name for this S12. This integral S12 is what's called the line strength. And if I square it, because it actually turns out it may be complex, this is what's called the intensity. Another term, and this is what an analytical chemist may call it. Sometimes it's called an extinction coefficient or an absorption coefficient. Right, so this integral, remember in Beer's law, analytical or instrumental, right? Beer's law tells you how much your sample absorbs, and it's the path length, roughly path length times the absorption coefficient. Right? All the absorption coefficient tells you is when light passes through your sample, what's the probability that a molecule, your sample is going to pick up a photon and get excited to the next level and absorb that photon. Right? That's all we're calculating. What's the probability that something in the ground state absorbs the photon and gets excited, therefore absorbs it? So this output of this integral is just the intensity of the line. It's how, in the vertical scale of your spectrum, remember the x scale is frequency or wavelength or energy, however you want to think about it. The y-axis is intensity. Sometimes it's absorption, sometimes it's emission, depends on what you're doing. That is always proportional to this integral. The output of this integral is built into the intensity of the line. Right? There are other factors that go into this as well, other than the absorption, but this is kind of the intrinsic intensity of a line. If a line's integral, if I take two states and calculate this and it goes to 0, I won't see that line in my spectrum. It's invisible. Blank. There's no probability that's going to get excited to the excited state. Right? We call that a forbidden transition. So this is not guaranteed to be 0, non-zero. And let me show you, there's exactly one situation, there's a couple situations in a particle in the box, but there's a really clear situation where this fails and you get a 0 out. And that's where we calculate the probability of interacting psi1 with the light and invoking no change. So again, this is just some numbers, 2 over L, epsilon E naught, cosine omega 1, 2t. 0 to L of sine pi x over L, x, sine pi x over L, dx, which is equal to just some numbers times 0 to L of x sine squared pi x over L dx. All right, it's not really clear what the result of this is. All right, so I'm going to do the same sheet kind of. I'm going to change my problem to minus L over 2 to L over 2 so I can use cosines instead. This is the same integral from minus L over 2 to L over 2. I've just shifted everything by pi over 2, which changes signs into cosines and vice versa. It's going to be x cosine squared pi x over L dx. And we can evaluate this on a computer, but I like to just graph this. Think about these two functions. They're bounded by L over 2 and minus L over 2. Right, so this is cosine squared, symmetric. And then we're multiplying it by an odd function x. Right, so the multiplication of these gives me a graph that's anti-symmetric about x equals 0. This. That's the product of those two. This is x cosine squared. And when I integrate that, I get a negative contribution that's equal and opposite to the positive contributions. So negative, the positive contribution. And therefore, this whole integral is 0. Right, so here's an instance where there's no probability of this event happening. Saying is that light in some sense is some connective tissue that connects me from one state to another. It never leads you back into the original state. Right? What that basically means that's a null event. Basically, it's not doing anything. Okay, so it should be 0. Light is not doing anything, right? Which means it's not interacting with the system. Right? It just passes right through. And of course, that may happen. And of course, what the point is that doesn't happen. The light interacts with the molecule. The molecule, if there's an available state at that frequency difference, it's going to transition at some probability. Now, it may have a very low probability. Probability of going from site to site 2 might be really, really tiny. But if it's non-zero, there's going to be some intensity. But the important thing is that light doesn't transform one molecule into the same state, right? It just doesn't interact, right? If it ever interacts, it's going to change the state. It always manipulates the state. Right, and it's not really worth doing the other calculations. Everything, if we think about psi 2 to psi 1, I'm just flipping the order of the signs. It's exactly the same calculation. Psi 2 to psi 2 is exactly the same as this. Odd times even 0. All right, so what do we see? Well, what we see is that light induces a change if delta n between the states that are connected by the light is equal to 1. We call these allowed, so this means that the allowed transitions, if you will, along this are say the 1 to 2, 2 to 3, 3 to 4, dot, dot, dot. The term we call this these are called allowed transitions. Term is allowed. We often sometimes call them bright transitions or bright states. I like allowed better. And it's not too hard to show, but if we do delta n equals 2, if say we go from the 1 to the 3rd level, or the 2nd to the 4th level, delta n equals 2, the integral is 0. Because the product of two wave functions that are separated by 2 ends are both even. N equals 1 is odd, even, n equals 2 is odd, n equals 3 is even. And so if I go from 1 to 3, I'm going to have a product of an even function times an even function, which is even, times x, which is odd. Overall odd and goes to 0. So any transition between n equals 2 levels, delta n equals 2, are forbidden. No change if delta n is equal to 2. So 2 to 4, 1 to 3, not allowed. These are called forbidden transitions. In fact, once you do the math, what you find is that for the particle in the box, the allowed transitions satisfy that delta n is equal to 2k plus 1, where k is a number. K is equal to 0. So the allowed transitions are delta n equals 1, 3, 5, 7, and so on and so forth. Right? So we'll see absorptions at energies where we connect two levels that are different by 2 quanta, or 1 quanta, or 5 quanta, or 7 quanta. Right? But it doesn't tell me how intense they are. Right? The integral tells me how intense they're going to be. The bigger the integral of these wave functions are times x, the more intense the line is going to be. And so even though 1, 3, 5, and 7 are all might be allowed, it doesn't mean that their integrals are going to be large. They're just non-zero. Right? So let me show you in the last 5 minutes. Actually, I got 10, but I'm going to finish a little early. Let me show you what this calculation looks like. Right? So let me. It's going to take me a second because I got pulled up. So yesterday I was extremely bored in a committee meeting and decided to write a little bit of code for this. Jupyter. And so what I've done is I've just basically written down a little code that calculates all the wave functions for a given part of the box, calculates all the possible frequency differences between the energy levels, and calculates the intensity, and then makes a spectrum. Okay, so it's just a little spectrum. It just solves this problem for us. So let me show you what I got. I'll try to zoom out. Okay. So I've got some code here that sets it up. So I've defined my box here. The length of the box is 10 angstroms. I've set it just for simplification to the maximum level that it thinks of is n equals 10. Okay, there are many more states, but I don't want to look at all of them. So it goes up to n equals 10. I've set the mass to the helium atom, right? So we've got a helium atom in a box of 10 angstroms. And then I define my energies and my wave functions. They're all just sine functions and things. Right. And so I get an energy levels. This is like the energy level spectrum of the molecule. Energy on this axis, and each one of these lines are the energy levels themselves. Right? And remember, they go as n squared, so the spacings get larger and larger as you go. So 1 and 2 are really close together. 2 and 3 are a little further apart. 3 and 4 are even further apart, and they start to spread like this. All right. So what my program does is it says, "Hey, I started at n equals 1. I'm going to have a transition between 1 and 2. Calculate the frequency of that and the intensity of it by doing the integral, which is 0. Delta n plus it's allowed. Delta equals 1 is allowed. It's going to do it for the next one, the next one, the next one, right? It's going to do all the transitions between all these levels in the ground state. And then it does for the next set, 2 to 3, 2 to 4, 2 to 5, and then 3 to 4, 3 to 5, and so on and so forth. Right? I'm just going to enumerate all the possible pairs, calculate the frequencies, bring their wave functions in, and calculate the integral. Right? And then I plot that on a spectrum. Intensity, which is the integral on the y-axis, versus the frequency of the line on the x-axis, which is just a spectrum. All right, I get a spectrum that looks like this. I've kind of roughly labeled these. Let me see if I can make the labels. It's not the most beautiful picture in the world. But as you can see, so remember the y-axis here is the integral result, the intensity. You can see my delta n equals 1 transitions are very strong. Here's the 1 to 2, the 2 to 3, the 3 to 4, the 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9. They're all very intense. And the reason why is because you're only moving, your wave function is only moving by 1 quantized frequency. Right? You're going from, for instance, 3 pi x over L to 2 pi x over L. In some sense, those wave functions look somewhat similar. When you integrate them, you're integrating the similarity between them, product them together and integrate the similarity, and they kind of look fairly similar. Right? They're both roughly the same frequency, a little slightly different. And so the integrals are fairly large for the delta n equals 1s. And then if you notice, there are no delta n equals 2s. The next line that shows up, which is very, very weak, are the delta n equals 3 lines. So if the delta n equals 2 lines were here, they would be somewhere in this region between the 1s and the 3s. There's nothing there. They're all gone. That's all those delta n equals 2 combinations are forbidden. The integrals are 0. They just don't appear on the spectrum. And so the next series that shows up are the delta n equals 3s, which is the 2 to 5, the 3 to 6, the 4 to 7, the 5 to 8, and so on and so forth. Right, and as you can see, they're much weaker. And that should make sense because now what I'm doing is comparing two different waves of very different frequencies, right? The n equals 5 wave oscillates much more rapidly than the n equals 2. So when you product them together, you don't get a lot of result. You don't get a lot of residual. So the intensities are much weaker. The two wave functions don't look very similar. But I get a series of them, and then eventually I get the next series, which is the n equals 5, right? Here's the 3 to 8. This is the 2 to 7 here. There's a 4 to 9 here. The 2 to 9, that's a delta n equals 7 line. Are you starting to see the trend? Right? I mean, I have these patterns that are specified by differences in delta n, and the intensities tell me something about the similarity between the initial and the final state. Now, just to convince you, what I've done is I've taken this plot and plotted it as a log plot on the Y scale, so you can see some difference. So this is what the spectrum looks like. Again, the most intense lines are the delta n equals 1. And then there's a series of delta n equals 3 lines that are intense, that are all kind of clumped up together. Again, the clumping is more spread out because these levels are more spread out. Weird dependence. And then that's done. And then I have the delta n equals 5s. There's only 2 of them up in max equals 2. And then there's the delta n equals 7s. If I add more transitions, we'll see more. You just do that. So I'll set the n max equals 20. Right, now I have more levels in my energy diagram. And you can see now it's spit out a bunch of lines. I'm actually having some integration errors here. But now I'm starting to get, it's not showing all of them, but so now I'm starting to see some of the delta n equals 1s here. There's 14 to 15. Here's a delta n equals 5. Here's a delta n equals 11. Delta n equals 15. And you see the patterns that are starting to appear? I have some glitch here. It's not showing me all mine. I think I know why, actually. I can no resolution. But anyway, you get my point, right? So there's this sense that there's these patterns that just arise from the symmetry of the system. Right? That we're alternating even and odd functions and we're using sine waves. You have a natural set of progressions that vary in intensity and also vary in structure, just because of the natural symmetries of sinusoidal and oscillatory functions. Right? Just as there's natural symmetry and these natural rules that appear from the structure of the molecule. We're probing the molecule's energies. The spacings of these tell me something about the spacings in the box. It tells me about the box. It tells me about the mass of the particle, right? I'm indirectly from these patterns learning something about the structure of the system itself, indirectly. That's what spectroscopy is. And so just one more final piece of jargon is that we have now shown that there are certain combinations of levels that are bright and certain combinations that are dark. And these rules specifying allowed and forbidden delta n's combinations are called selection rules. Every spectrum has a series of selection rules, and the selection rules vary on the problem. We're going to see a series of, oh, sorry, not selection series. Sorry, talking too much. Selection rules. All right, we're going to find that, say, in the hydrogen atom, the allowed electronic transitions, it's like, say, a 1s electron to some other level, has to satisfy specific rules. For instance, a 1s electron can't go into the 2s state. It has to go into a p state. 1s to 2p is allowed, but 1s to 2s is forbidden. Right? So every balanced system has a set of selection rules, which just arise from the symmetries of the wave. It's just the similarity of the wave functions, how they evolve, how they look different at different energy levels. That's what determines the brightness of the transition. And so every time we come up with a new technique, a new model, we're going to have to ask the question, what's the spectroscopy look like? What do we expect the selection rules? And that's going to teach us a lot about the molecule
It's gonna teach us what we expect to see, put it in our system, in our spectrometer, and will help us to interpret the spectrum. Okay. So that's our introduction to spectroscopy. Every time we do a new model, the bond and the hydrogen atom, the molecule, we'll come back to this conversation. What are the selection rules? Right? And that tells us everything about the spectroscopy, and then we can start doing experiments. Right? Interpreting experiment here is by understanding the selection. All right, have a lovely weekend, everybody. Start a new project. Come on, next week.
A Discord message from Molly in the middle of class being like, hey, the fluorimeter's not connecting to the computer. How do I fix it?
Wait, what's not connecting?
The fluorimeter for
Oh,
instrumental.
She's upstairs.
Yeah. She's like, are you in the lab right now? I'm like, no, I'm downstairs in Pika. I was like, unplug it, plug it back in. While it's unplugged, I'll